So this is a little bit confusing till now, because I think we can come back to it after we run it in practice, and then things will make a bit more sense. So we have this data set of the iris, and it has 4 things were measured, 4 variables: sepal length, width, petal length, and width, 50 flowers, individual flowers from 3 species. Okay, so we have this species, this one, and that one. And the aim of the PCA is to represent as much variance as possible on the first few axes. So we don't actually have to deal with 4 things. We can simplify this, right? So the idea is to reduce the dimensionality. So from going from 4 dimensions, maybe we can reduce this. So the first step would be to organize our data as an m times n matrix, right? We spoke about m times n, where we have m are the dimensions, okay, the number of measurement types. So we measure the length, the width of these flower bits. And n is the number of replicates that we have. Okay, this is 10 per the species, and there were more species, so I think there are more, and so this would go down into different species. So we have n length of m measurements. Now I start by thinking about it I'm going to do everything in the 2-dimensional space so that we can see it, right? But of course we're working in 4 dimensions. And the first step is of the principal component analysis is to move everything to the center. And we do that by subtracting the mean from our data. So instead of talking about, instead of having things going from 1 to 7, I don't want my axis to be down there. I'm going to move everything to the center. Okay, so I'm going to subtract the mean. And now I have the mean value is like my 0, 0. And I take everything. Remember, like we did with anomalies. So now I've moved the center of my coordinate system to the mean of the data. And now I'm going to calculate the eigenvectors and eigenvalues of the covariance matrix so that I can rotate it to find these new dimensions. Now, we started talking about the linear algebra of this, but I really need you to understand that while you can understand it, this is not what you need to do on an everyday kind of using a PCA exercise. So to let's say wine. Okay, wine has character. We rank wines by we have competitions, and that is actually a great example of a multivariate data set. We measure a lot of different things in wine. How do we best characterize it? So we have the aroma, we have the bouquet, we have all sorts of things to do with the scent of the wine. We have things to do with the clarity and the color of the wine. So the amount of sedimentation in the wine. So we have so many different characteristics, it becomes almost impossible to compare them. So this is a good example of things that are multidimensional that we want to reduce the dimensionality. And a lot of things are redundant. If I think about the different things of scent-based things, some of them are quite redundant. Some of them say the same thing with a slight variation. So if I had a covariance matrix, I'll find that these things have high covariances. I can start thinking about these redundancies and try to generate a new set of wine characteristics called principal component 1, principal component 2, and so on and so forth, that have as little as possible redundancy in them. So PC1 and PC2 are not saying the same thing at all. And like we said, we do this by first finding the direction of the most variation in our data. So principal component 1 is really just capturing is an axis that is placed along the variance in the data to capture as much variance as possible. So if I put it up here, all my dots are, each one is falling on a different part of the axis. I'm spreading them out beautifully. The next step is, so I've placed the center of my axes here in the mean. Now what I want to do is, this is now going to be PC1, and I'm going to rotate. And again, I'm rotating only in 2D here, but I mean, like, in reality, these eigenvectors go through all 4 dimensions, right? I'm rotating with those vectors by using the dot product, right? I'm rotating my original vectors with the principal components to generate a new set of dimensions, PC1, PC2, PC3, that capture the variance. Okay, so I've orthogonized my covariance matrix, and this is what it looks like graphically. So I have principal component 1, which is determined this way, and that is along the highest variability, and it is normalized in the m-dimensional space along which the variance is maximized. So here we're seeing a 2-dimensional space, because we really can't draw better than that. But this is happening in the m-dimensional space, in our case 4-dimensional. And I'm looking for where the variance is maximized, and I've locked in principal component 1. Okay, and I've done this rotation using eigenvectors of the covariance matrix of the original data set. Okay, and these are the principal components. So I have PC1, and then everything else is coming at 90 degrees. The next step is to apply, so I can scale a vector, I can rotate the vector, and I can scale the vector. Now I'm rescaling these vectors to maximize differences in variation along each axis. So if I'm looking at PC1 and it's nice and stretched, PC2, I can do a little bit to resolve differences between the points by stretching PC2, so applying some sort of rescaling. Remember, I can do these 2 things to the vector. I can rotate it, and I can just multiply it. I can scale it. So we have, that is the next step. So now I have variances associated with each principal component, and the more the principal component explains the variance, okay, the higher its relative importance. So PC1 is stretching the data a lot. It is very important. PC2 is stretching the data less. It has lesser relative importance. PC3, I don't know if it's doing anything. PC4, all of those. I've had, in this case, there are only 2 dimensions because I've reduced my data set for graphic purposes. So I'm going to generate only 2 PCs. So the number of principal components that you generate is the same as the number of M's in your matrix. So this is called an ordination, and I can do 2 types of ordination. I can use an unconstrained or a constrained ordination, and it really comes down to the types of questions you're asking. So I can take a data set, say a time series, sea surface temperature analysis, we'll see in a minute, and extract axes based on variables within that time series. So I can just look at changes over time and find whether time is the best axis to describe my data set, or is there something else in the data set that is a better fit to maximize variance. And we'll see that in a minute. It'll make more sense. Constrained ordination is what is more intuitive, is extracting information from the data set to be explained by an external variable. So I want to see how this ordination is affected by, say, the depth I took the plankton from, or whether there was pollution in the ocean, if there's an oil spill or not, and how that affects PC1 and PC2.